Hey students, welcome back. We have been looking at applications of the integral the last few days. We looked at one application, that's the area between two curves. We've also used it to study volumes. So far we've looked at some geometric applications. Now we want to look at a physical application. And so we're going to start off with a definition. If an object moves a distance d, in a straight line, due to a constant force, so let's say a force of constant magnitude, capital F, then the work, so we're defining this concept of work, the work done by the force is capital W equals force, so F, times distance. So work equals force times distance. We'll need this definition here, right? This is the definition of work. Work is the force times the distance. Now the units for measuring force, that's going to depend on whether we're working with the metric system or the US system. So in the metric system, force is typically measured in newtons, distance in meters. So the basic unit of work would then be a Newton meter. And Newton meter actually has a name, so we're not going to use Newton meters. So a Newton meter is equal to a joule. And so the basic, or the measurement of work when we're working in the metric system is the joule. In the US system, it's the foot-pound. Right? So we've got distance here, and force is measured in pounds, so the foot-pound is the standard measurement of work in the US system. We'll need one fact also, and this is Newton's second law, the one fact from physics. Newton's second law, and that is that force is equal to mass times acceleration. All right, so probably most of you, if you've had a physics class, you've heard that equation before. Force equals mass times distance. Mass times acceleration, and we'll need that. So let's do an example. So let's say if a mass of 12 kilograms is lifted from the ground to a height of 4 meters, what is the work? Done. So how much work is required to get this mass, this object, from 12 kilograms, from 4 meters, geez, I'm stumbling over my words here, a mass of 12 kilograms lifted, starting at the ground and lifted to a height of 4 meters. So we're going to need one fact here, right? In this case, then, the only thing that we need to overcome is gravity, right? So we're going to look at the force required to lift and overcome the force of gravity. And so we'll need this fact, G is equal to 0.8 meters per second squared. That's the acceleration due to gravity, right? So here's our gravitational constant. And so in this case then, the force is equal to the mass, which is 12, times the acceleration due to gravity, that's 9.8. And so the work is going to be 12 times 9.8 times 4. I multiplied this out, it comes out to be 470.4 joules. Right. So here's force, and there's distance. In the case that you have a constant force, you just multiply force times distance, that will give us the work. In the example that we just did, the force was constant. We didn't need calculus, right, to solve that problem. It's just multiplication, right? Force times distance gives us the work. Now what we want to look at is the situation where there's non-constant force. So, so let's say, suppose that the force at position x, so at x, on an object moving in a straight line. And here, I want to think of this straight line, just think of it as the x-axis. So we've got a force acting on an object at position x, right, and this object's moving in a straight line, is given by, oh, and I should say from, let's say, point A to B, is given by f of x, where f of x is continuous. So here's the picture. Here's our x-axis. We've got point A, we've got point B, and we've got some object moving in this straight line. And so at every point x, we've got a force f of x acting on that force. And eventually, our object gets to point B. Right, so at every point x, we've got a force acting on the object. Now, examples of non-constant force, let's say that you're walking and the wind is blowing. Right? So you walk along, sometimes maybe the wind isn't blowing too hard, doesn't take a whole lot of effort to walk against it, and then a big gust comes, right? The force blowing against you increases, right? So there's lots of examples of non-constant force. There's one that I just gave you. Okay, now here's what we would like to do. We would like to find the force, the work done by the force in this setting right here. So the work done by the force in moving this object, or as this object moves from A to B. The process is going to be the usual one. Step one, I want to partition the interval AB as usual, so A equals x0 less than x1 less than dot 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 less than x of n, which is equal to b. Right? So we chop our interval up into a bunch of pieces. Second step, as usual, we want to choose. So let's choose xi star in the subinterval x sub I minus 1 to x sub I. Now, here's the point. We've required that our function f of x is continuous. Now, and let me sort of blow this picture up a little bit, right? So here's A, here's B. We've chopped our interval up into some pieces. We've chosen a point, so this would be x1 star right there, maybe x2 star is here. x3 star, doesn't matter where we choose it. Oh, so there would be an x4 star. Now, the point, the reason that we required our function to be continuous is right here. Continuous functions don't change drastically over small regions. So if this interval is fairly small, then the force occurring within this interval, yeah, it's non-constant, but it doesn't change a whole lot. And so in this case, I'm still working on step 2 here. And we can say since f of x is continuous, what we know is that f of x is approximately equal to f of x I star for all x sub I minus 1 less than or equal to x sub I, just x, less than or equal to x sub I. So the point is, as you are inside a particular subinterval, the force does not change very much, and so the force at position x here is pretty close to the force at x1 star. And so we can then approximate the force along each subinterval by saying it's approximately equal to f of xi star. Yeah. So continuing on this, we can say, thus, the work done along the subinterval from x sub I minus 1 to x sub I is approximated as, let's call it w sub I, it's approximately equal to fxi star times the length of that subinterval, which we call delta x. Right, so the work is approximately equal to f of xi star times delta x. So, the total work, capital W, is approximately equal to the sum of all these little works right here, right? So it'd be sum I equals 1 to n of w sub I. Just add up each of the w sub i's. That'll give us an approximation of the total work required, or the total work done along the interval from A to B. And then if we fill in the blanks here, that's equal to sum I equals 1 to n f xi star times delta x. Now we've got a Riemann sum. That's a continuous function right here. And so that means that the work is going to be the limit of the Riemann sum. So limit as n goes to infinity. Sum I equals 1 to n f xi star delta x. And because we've got a continuous function, we can compute this as a definite integral. So, if we have a function that describes the force at each position along the interval, then to find the work done by that force, you just integrate the force function. Now, we're going to apply this principle in a few different settings, a few different types of applications. So the first type of application that I want to look at, springs. Now, everything that we need to know about springs is governed by what's called Hooke's law. So Hooke's law goes like this. Get this right? Yeah, the force required to hold a spring stretched at a length, say x units from the natural length is, let's put it down here, is proportional to x. All right, so the force required, I almost said work accidentally, the force required to hold the spring stretched at a length x units from the natural length. That's one thing to remember. Whenever you're working with springs, you work with the natural length. It's proportional to x. And so that can be written in equation form. The force at x is k times x. Proportional to x means it's a constant multiple of x. So anytime you have a spring, there's this constant capital K that's associated with that given spring, right? And each spring has a different constant. And the picture is something like this. So let's say you've got your spring, right? And here's natural length. And then you stretch that spring x units from its natural length, right? There's a given force required to hold it in that position. What is it? It requires k times x newtons or pounds, depending on which you're working with, right, to hold it stretched in that position. Okay, so let's just try an example now. A spring has natural length 20 centimeters. A force of 25 newtons is required to hold the spring at 30 centimeters. So hold the spring at 30 centimeters. Let's find the work. Done in stretching from 25 to 30. So 25 centimeters to 30 centimeters. Okay, since we're working with a spring, we go with Hooke's law. And so the first thing you always need to do when you're working with springs is you need to figure out what the spring constant is for this particular spring. So we start off just with this equation, f of x equals k times x, and our first job is to figure out what k is. Okay, so let's see. In this problem, there should be something that allows us to find that out. And here it is right here. A force of 25 newtons is required to hold the spring at 30 centimeters. And by the way, that's 10 centimeters past its natural length. Now we have to be careful here. When you're doing work, the unit is joules. A joule is equal to a Newton meter, so we've got to get our units right here. We've been given information in centimeters. We need to convert all of that to meters. So what we know is that 25 newtons is equal to K times X. This is 10 centimeters, 30 centimeters is 10 centimeters past its natural length, which is 0.1 meters. Right? So work in meters when you're doing work. That was a bad sentence. Use meters when you're doing work. So that means that K, our spring constant, equals 250. So now Hooke's law tells us that for this particular spring, f of x is equal to 250 times x. Now we want to find work. We want to find work done in stretching the spring from 25 to 30 centimeters. So the work is going to be, remember what we showed, we've got our force function. To find work, you integrate the force function. The limits of integration are going to correspond to, remember this is 5 centimeters past its natural length. This is 10 centimeters. So the limits of integration here will be 0.05 and 0.1. And then we have 250 x dx. If you want to compute work, integrate the force function. That's equal to 250 x squared over 2, where we go from 0.05 to 0.1. That is 125 x squared, go from 0.05 to 0.1. And I worked this one out, so it actually comes out to be 0.46875 joules. Okay. So that's a spring problem, and you'll have some examples or some spring problems in your homework. Okay, the next application goes under the category chains. And so here's the idea. You've got some chain, some heavy chain made out of some type of metal, and it's hanging over the edge of a building. And now what we want to do is we want to reel this chain back up, right, over the, so it's all up on the top of the building. And so notice, as you start pulling, right, when at the very beginning, you've got all this chain hanging down there, it's very heavy. But as you start pulling this chain up, you can rest some of it on the building, there's less chain to pull up, it gets lighter as you go. Right, so this is another example of a non-constant force situation. So here we go. A chain, and I'm just going to jump in with an example, a chain weighing 4 pounds per foot is 100 feet long and hangs over the edge of a building. Find the work done in lifting the chain to the top. Now, it's important, we went through a derivation that shows that if you have a force function, then to compute the work, you integrate the force function. Sometimes that works out nicely, but not all of these problems work in the same way. So you want to understand the derivation, but you also want to understand the definition of work. And so here's our picture. Here's our building. Here's our chain hanging over the edge. And so I'm going to give myself an axis. I guess I'm going to put 0 here and 100 here. Now, so here's my chain. It's 100 feet long, hanging over the edge of the building. And here's the idea. What I want to do is I'd like to chop this chain up into a bunch of pieces, a bunch of segments, each of length delta x. So if we have a segment at position x, here's the idea. So a segment of length delta x weighs 4 delta x pounds. There's our force right there. Now, how far does this particular segment need to travel to get up to the top? Right, this segment travels x units. I guess we're working in feet here, so it should be x feet to the top. So the way we want to attack this problem is to find the work required to move an individual segment to the top, and then just imagine if we chopped our chain up into a bunch of pieces, we will find the work required to get each of those segments to the top. That will give us our function to integrate. So the work done, or the work, the work needed to lift this segment to the top is force times distance, so that's going to be 4 times delta x times x. So, the total work is going to be the integral from 0 to 100, 4x dx, right? Once we have a formula that tells us the work required to do one little piece of the work, then we integrate, right, to find the total work. So this is going to be a 2x squared going, x squared going from 0 to 100. What is this, 20,000? And we're working in the US system now, so this would be foot-pounds. Okay, so we've seen 2 examples of doing work, and then I'm going to stop here and we're going to pick up with this idea in the next lecture, right? You need to be flexible. There are certain situations where you're going to be given the problem in such a way that you can actually extract who the force function is. In that case, you can just integrate. But you need to understand our original derivation, right? Because not every problem, in particular these chain problems, are not given in that same way, right? The force involved the delta x, and in this case, the distance was our x. Okay, so we'll pick up with this and do more examples in the next lecture.